First of all, thank you. And on more technical side of things, I would like to talk to you about the innovation in terms of when it comes to implementation of real storage systems on board maritime vessels or in any sort of means of transportation, I would like to say. When it comes to the use of gaseous hydrogen, the good news is that we are, you probably know, probably not, that we can achieve the required energy density when it comes to higher pressures, for example, 70 megapascal, and the current storage vessels allow for increase of that pressure to 90, 100 megapascals. And the good news is that we are able to help to lift a certain number of barriers on the way to adopting such vessels on board marine vessels. So one of such technologies will be Microleaks and burst safety technology, and I'll be specifically talking about the fire safety side of things, because we know that hydrogen storage tanks, they are it's a very mature technology. They're durable, they're robust from a mechanical point of view, and there are probably no issues except for maybe leaks and connections and things like that there. But there's a list of questions that are still not answered when it comes to the fire safety. So I'm just here giving you a list of abbreviations that I'll be juggling with during the presentation. I'll try to keep my timing because Rachel told me I'll be left without lunch if I don't keep the timing. So I'll try to be very...
I have my timer here.
So most importantly, what you should be probably paying attention to is the Microleaks burst. Probably doesn't see my pointer. Microleaks burst, which is the name of the technology we've given to and adopted in Type 4 specifically, composite storage tanks with plastic liners. And also I will be talking a lot about the fire resistance rating of these tanks. And yeah, some of the terms you already probably know, such as TPRD is a thermally activated pressure relief device. The good news is that the technology allows for the use of pressure vessels in any application without TPRDs. And we know there's a lot of issues associated with pressure relief devices and valves and things like that there, in terms of them being faulty in some situations. We have a limited knowledge about their operation when it comes to maritime and shipping. But we do know there is a problem with them when it comes to, for example, rail applications. They can activate suddenly and in a very unwanted situation from a vibration, for instance, when the tanks are, this whole storage system is installed on the top of a car, for example, or locomotive. So when it comes to scenarios when we have to implement this technology, it's obviously a real incident. And before that, all the storage systems are produced, validated, and tested in testing laboratories prior to being enrolled in the market, or prior to be admitted for type approval or full certification. So there's a list of scenarios when the technology can be handy and when it can be and must be applied. It's smoldering fires. There are scenarios when CNG tanks, luckily not hydrogen yet, exploded. Even though there were pressure relief valves, there were measures in place. However, the smoldering fire just thermally degraded the storage, and therefore the pressure exerted on the system was too high, so the system failed, and the whole garbage truck, for example, exploded and damaged to neighboring houses and infrastructure. There are other types of fires that we should be mindful of. For example, vehicle tire fires, or just any vehicle fires, gasoline and diesel spill fires, which could be resultant from a collision or any incident, including in maritime sector as well. And also breakage of the piping, which is another problem, which could lead, if it's especially a high pressure piping, which could lead to ignition of the hydrogen jet erupting from the full bore rupture, for example, and it can impinge neighboring tanks. And there are measures that are in place, implemented by industries, but we do know there are problems there, unfortunately, such as thermal activated pressure relief devices that I've mentioned already, intumescent paint. Essentially, you probably know what it is. It's a paint that is swelling under elevated temperatures, then it's charring and providing a barrier to heat transfer to the system or to the structure of the building, for example. And the third is what we are talking today about, is the self-venting TPRD-less tanks that can withstand any sort of fire and that will just self-vent and provide the safe blowdown of hydrogen gas in a controlled manner without explosion. Just a few examples of what sort of intensities of real fires we can expect, and one of the examples would be spill fires of liquid fuel, such as gasoline or diesel. If there's an ignition source present, it can produce a very high specific heat release rate, which is the overall heat release rate from a fire produced by combusting fuel. And if you divide that value by the area of the spill or the fire source, that's your specific heat release rate. And these values are typically a lot higher than what you can expect from a laboratory scale testing that all storage systems must undergo before being implemented in real applications, including maritime transport. So I won't stop too much here. I just want to explain that on the left-hand side, if you look at the graph, first of all, on y-axis you see the specific heat release rate that I mentioned, and on x-axis you see, on x-axis you see the specific heat release rate, and y-axis you see the fire resistance rating. That's the time until the fire starts, from the moment the fire starts affecting the system until it fails catastrophically in a fire, producing blast wave, fireballs, projectiles emanating tens of meters and can damage, can injure people and damage infrastructure. So the laboratory scale fires are usually operating in the red area. If you see the red arrow, it's when the scatter is the highest. So the predictability of the performance of the system is very non-reproducible, let's put it this way. And the real fires are producing the situation that is covered by the arrow on the right-hand side, the blue arrow. That's when the saturation happens, and that's where the time to tank explosion would be very, very short. And that just explains where the reality is, around 5-6 minutes. That's the time until the tank will rupture in reality. So a few examples of what can happen. Obviously, on the right-hand side, you see a very catastrophic and horrendous scenario, which could be a case in case there is a alternative fuel on board an aircraft. On left-hand side, another type of application, which would be just a passenger car. In both cases, we can see that there's a possibility for the tanks to be affected by a fire. Obviously, such scenarios can propagate and spill over to maritime applications. So I tried to put it in very simple terms and explain the main difference between the failure mechanisms of standard and micro LNB tanks. So left-hand side, you see the load-bearing wall fraction and the decomposition front moving towards each other, and the melting front of the liner, or the melting of the liner, is essentially the moment when the gas will start leaking. On right-hand side, the difference between these two, the right-hand side explains the introduction of the green layer, or substitution of one of the layers, a composite that provides liner melting before these two fronts meet each other and before tank ruptures. And this is one of the cases of our validation that we had previously with a small-scale 7-liter 70 megapascal tank, which underwent a standard, well, it's actually standard but not standard, because the intensity of the fire was equivalent to a realistic fire scenario. And at a certain point, you'll see that leak will happen. There's a pressure drop. However, there's no visible large flames, as you would see from a TPRD when the hydrogen jet will be erupting from the nozzle. I'll just give you a moment to see that. And I will wait for the entire video, but just to give you an idea. So that's when the pressure will start dropping, leak starts, but there's no change in flame envelope, essentially. And we managed to predict, by using our models in-house, we managed to predict temperature and pressure dynamics inside the tank as well. I'll be running through the presentation quicker because I've been given a 5-minute notice. So another way of looking at it is firefighters and first responders, when they arrive on the scene of incident, they must have a possibility to operate as usual, to extinguish the flame, to put out a fire, help people evacuate. And for this reason, we tried to validate technology in the range of tests where the fire was put out, the flame was extinguished, and we still proved that technology works and pressure drops to atmospheric without any problem. So the tank wasn't, the tank remained intact essentially and did not explode. Just want to briefly show you this. This is obviously a speeded up video, probably 12 times. At the end of the day, the fire is put out and the tank remained intact. And another experiment showed the termination of the burner, leakage of the tank, hydrogen dropped to atmospheric, not in this particular graph, it dropped probably to 30 bar, but eventually it dropped to atmospheric and the test completed successfully and tank blew down safely. Another experiment that we conducted in Norway, and these are our, again, predictions of pressure and temperature. Impinging jet fire. This is one of the most important bits I wanted to show. Snapshots of impinging jet fire from a 70 megapascal, another tank impinging this one. And you see the aftermath on the left-hand side. The outer layers of composite melted, but the tank remained intact and pressure dropped to atmospheric safely. I'll probably skip the video because I'm afraid we are a bit late. By we, I mean me. 1 minute. So that should be good enough for me to finish on conclusions. So we're happy enough to say that we were able to develop this technology and to come from a very low tier level of the concept until the validation in relevant conditions. So we'd probably say it's at a stage of probably 4, 5. Technology allows for any composite vessels for hydrogen, and not only hydrogen, it works well for any gaseous substances, including, say, CNG. So methane can be stored safely and tested safely in any fire conditions, including spill fires, including impinging jet fires, smoldering fires, etc. Most importantly, it helps to eliminate consequences from a catastrophic failure of any hydrogen tank, such as blast waves, fireballs, projectiles. It allows to prevent also the so-called pressure peaking phenomenon when you have a release of hydrogen in a confined space, like a room, or under the deck of the vessel. And it can be applied to any means of transportation, even stationary applications such as hydrogen refueling station, for instance. So that would be me. Sorry if I'm taking more than it should be. Thank you.